All right, today we got parametric functions. We're going to do the calculus on parametric equations now. So we start with the first and the second derivative. So if x and y are both differentiable functions of t, and if dx dt does not equal 0, because it's in the denominator, then the derivative of y, or dy dx, is derivative of y over derivative of x. Now, these differentials, they kind of work like variables where you could multiply the top and bottom by dt, and that's where you would get dy dx out of that. Of course, we're not going to do that, but that's kind of how it works. The second derivative has a little catch to it. They're saying that, well, when you take the derivative of y, the function y, you do dy over dx. But when you take the derivative of the derivative, when you take the derivative of y, you do dy over dx again. So you have to keep dividing by dx dt every time you do a new derivative. So there's a little extra piece to it that I'll show you here in this example. Consider the curve defined parametrically by x and y for 0 to pi. A. Sketch a graph of the curve in the viewing window -7 to 7 to -4 to 4. Indicate direction in which it is traced. The only time we graph these by hand is yesterday. That's it. The rest of the time we're going to be using calculators to graph these. So grab your calculators. You'll want to play along. I don't think the test is the first time you want to be trying these calculators and trying to get answers. We need to practice it. All right, here we go. So we're going to go a mode. We're going to go to parametric. And then y equals. So parametric mode, parametric, we'll go to y equals and we'll put in t squared minus 5 and 2 sine t. The window we want from 0 to pi. And then it tells us that the x's go from -7 to 7. And, whoops, I want to go by ones there. And y's are -4 to 4. Did I go too fast? Everybody good? I'll help you if I went too fast there. Okay. Then we graph it. On the very left-hand side, it looks like 1, 2, 3, 4, 5. It looks like -5 to 1, 2, 3, 4, 5. So 5's on each, 2, 3, 4, 5, 1, 2, 3, 4, 5. And it looks like the highest is up around 2. So it does something like, I'm going to do something like that. And if I remember right, it graphed from left to right. B, find the highest point on the curve. Well, it's the y's that determine up and down. So we want to maximize the y. So dy dt is equal to 2 cosine of t, the derivative of y. So we take the derivative, set that equal to 0. Well, we're only going from 0 to pi on the t's, and cosine is 0 at pi over 2. So t is equal to pi over 2. That's going to maximize the y. But it says find the highest point. So now we're going to plug pi over 2 in for the t's here. But I don't know what pi over 2 squared is, so we're going to use a calculator to find those. So we can go pi divided by 2 squared, and then minus 5. So -2 point something, -2.532, and then pi over 2 in for sine is 1, and that's 2. So there's the highest point. Now I could have gotten that just from the graph. Watch this. We go second, calculate a value, and I would just put in pi divided by 2, and we would get the exact same answer, -2.532, 2. C. Find all points of inflection on the curve, justify your answer, which means now we're taking the second derivative. So let's get the first derivative, dy dx. Well, we got the dy, 2 cosine, over dx dt would be 2t. There's the first derivative. And those 2's will cancel out. We can cancel as we go. d2y dx2 now is bottom times derivative of the top minus the top times the derivative of the bottom, which is 1, all over t squared. Now that's the derivative of the derivative, but we said every time you do the derivative, it's over dx dt. I did the dy dt, I need the dx dt. So this is over, here's your little extra piece, over dx dt again. So that's going to be over 2t. That's the little extra piece that several of you may or may not forget for the test. I'm trying to emphasize it, I'll review it, I'll remind you, and hopefully we don't forget on the test. Well, we can multiply, instead of dividing by 2t, oh, where did I get 2t? I wanted, oh yeah, up here, 2t. Instead of dividing by 2t, I can multiply by the reciprocal. So instead of dividing, we can multiply by the reciprocal. So we get negative t sine of t minus cosine of t over, it ends up being 2t to the third when we're done. Now let's not forget what we're trying to do. We're trying to find the point of inflection. So we want to know where this is 0. Well, you wouldn't be able to solve that by hand. That's going to be a decimal value. Not only that, this is not a parametric equation anymore. We're just trying to solve this one single equation. So let's get out of here. Let's go back to function, because we're not solving a parametric equation. We're solving one single equation. Go to y equals negative t sine of t, or x's in this case, minus cosine of t. But keep in mind that we're solving this for t is 0 to pi. So that's where we're looking, right there. And we don't want to go past that. So window, I want to go from 0 to pi. I don't want any other distractions. I don't want any other zeros that might interfere with this. Yours are probably negative. Oh, maybe yours are still these. Anyway, graph. And there's the 0 right there. So we'll go second, calculate a 0. And we'll get over there. Enter. To the right. Back up. It says guess. 2.798. So t equals 2.798. But it says point of inflection, right? Find the points of inflection on the curve. And so we need to plug that into the original equation. So we have, see, I calculated the value, so x holds that. So now I can just do x squared minus 5. There's the x coordinate, 2.830. And the y is 2 sine. So I can go 2 sine of x. And it's 0.673. 0.673. Well, here, you don't have to do this. I'm going to go back to this. Kind of switching back and forth here. If I go y equals, no, graph. There's the curve. Oh, we changed the window. Gosh darn it. 0 to pi, I think it was negative 7 to 7. All right, there's what we originally had. Now if you go second, calculate a value, and I'll go 2.798. Keep in mind that's rounded. So there's our point of inflection, 2.830. This says 2.828 because I have a rounded answer. Then 0.673. That's where the point of inflection is happening right there. So that's what we found. Arc length. When we did arc length before, we talked about, well, we're going to talk about the same thing, Pythagorean theorem. If you have this curve right here, and we want to estimate the length, what we could do is we could make this big. We could go change in x, change in y, and we could use this hypotenuse to find the length of that curve, to estimate the length of the curve. That'd be a horrible estimate. We could make it better. We could go two triangles and do two hypotenuses. We could make it better. We could go 1, 2, 3. We could go 4 triangles. We could go 1 billion triangles. We could go 1 trillion triangles. And those little hypotenuses would get closer and closer and closer to the curve. Well, that's what integral does. It's an infinite amount of something where the length is infinitely small. So that's where you get this, right here. But you have the derivative is the change in x. The derivative is the change in y. So you have to do the derivative squareds in all of those. So let's try this with example 3. Find the length of the asteroid. We need dx dt is 3 cosine squared t times negative sine t. There's the derivative of x. It's very easy to plug the function in and square it, to forget to do the derivative part. It's very easy to do that. You can't forget to do the derivative. dy dt is 3 sine squared t times cosine t. Now we're going to use that in the Pythagorean theorem. We're going to integrate from 0 to 2 pi square root of 9 cosine to the 4th t sine squared t. So I squared that. And when you square that negative, it goes away. It becomes positive. That's why I don't have a negative in there anymore. And then we want to square this, which is 9 sine to the 4th t cosine squared t, and then dt. If I give you a problem where you can get rid of the radical, or what's under the radical is linear, then we can do this by hand. If you can't get rid of the radical, then that'll be a calculator problem. Here we can get rid of the radical, believe it or not. We can factor out of each of these, first of all, a 9. We can factor out a sine squared, because this has a sine squared, that has a sine squared. So I can factor out sine squared t, and we can factor out cosine squared t from both of these. Now what's left is, if I get rid of the 9, get rid of the sine squared, and get rid of 2 of these, and 2 are left, this is cosine squared. 9's gone. I factored out the cosine squared, factored out a sine squared, but there's a sine squared left. All right, you see what I see? Go ahead, Matt. Yeah, so this piece is 1. Not only that, when we say, well, that's 1, what's left is all perfect squares. So it's 3 sine cosine. So that's why we're going to do this one by hand, because we can get rid of the radical. Well, now we have u substitution. We're going to let u equal, I would let it equal sine of t. So du is cosine of t dt. Now we have this 3 out here. I'll just kind of pull that out here. Now it's integral of u du. Because cosine dt becomes du, sine of t just becomes u. This is 3 times 1/2 u squared. In other words, 3 halves. U is sine. Sine of t from 0 to 2 pi. So we have 3/2 times sine of 2 pi minus sine of 0. And you run into a problem. Sine of 2 pi is 0, sine of 0 is 0, so you end up with 3/2 times 0, and you end up with a length of 0. That's not true. So what's happening is all of the positive area is canceling out with all of the negative area as you go around this object. So we have to approach it in a slightly different way. And what we notice here from 0 to pi over 2 is one branch of it. As a matter of fact, they have 4 branches, let's say, and they all seem to be symmetric, and they are. We can assume they are. So we have to go down here and make a little adjustment. The adjustment has to happen right here. Instead of going from 0 to 2 pi, we'll multiply this times 4 and go from 0 to pi over 2 so that we don't end up with an answer of 0. 0 makes sense for the integral part, but it doesn't make any sense for the length of the curve. The curve exists. What's that going to be? 6? Sine of pi over 2 minus sine of 0. Sine of pi over 2 is 1, so the answer ends up being 6. It's not 0. We have to make a little adjustment for it to make sense. Might have to employ that little trick if you get an answer of 0. You got to figure out some symmetry. Maybe it's only symmetry on a half of it, so maybe you multiply by 2, maybe you have to multiply by 3. Good chance you won't see that very often, but you might. We're not going to, we don't do problems 20, 30 times like we would in Algebra 1 or even Algebra 2. We only do these a few times, as you've noticed throughout the year. So I thought we kind of have a little bit of time to talk about dividing by dx dt one more time. And he just, instead of me saying it, he does a good job of explaining this. So let's listen to Mr. Kahn.
Into these functions and then plot the corresponding x and y's for each t, this will plot a curve in the xy plane. What I want to do in this video is figure out the first derivative of y with respect to x and the second derivative of y with respect to x. And in both cases, it's going to be in terms of t. So let's get to it. So first, let's find the first derivative of y with respect to x. First derivative of y with respect to x. And we've seen this before in other videos, where this is going to be the derivative of y with respect to t over the derivative of x with respect to t. And so this is going to be equal to, well, what is the derivative of y with respect to t? dy dt is equal to, let's see, the derivative of e to...
I like how detailed he is, but if you're looking up a video on the derivative of parametric equations, you probably know what the derivative of e to the t is. So I wish he'd pick up the pace a little bit, but he is detailed. It's good.
The 3t with respect to 3t is just e to the 3t. And then the derivative of 3t with respect to t is going to be 3. So I can say times 3.
Yeah, but don't put it there.
Or
yeah, there you go.
Put that 3 out front.
Yeah.
And then the derivative of -1, well, a constant doesn't change. No
we know.
To your t, so that's just going to be 0. So that's dy dt.
Like, pick up the pace. We know what the derivative of -1 is.
E to the 3t, all of that over, well, what's the derivative of x with respect to t? Derivative of x with respect to t is equal to, well, we're going to have the 3 out front, and so the derivative of e to the 2t with respect to 2t is going to be e to the 2t, and then we're going to take the derivative of 2t with respect to t, which is just 2, so this is going to be 6e to the 2t. 6e to the 6e to the 2t. And let's see, we could simplify this.
Yeah, so now you can simplify as you go. That's fine. Matter of fact, we encourage that because then your second derivative is going to be easier.
This is going to be 1/2. That's 3 over 6.
Yeah.
E to the 3t minus 2t. 3t minus 2t. And I'm just using exponent properties right over here. If I have 3 t's and I take away 2 of those t's, I'm just going to have a t. So this is just going to simplify to a t right over here. So
now, of course, your second derivative is going to be much easier because before you're probably looking at quotient rule. Now you're just looking at, well, it's e to the t. It's 1/2 e to the t.
So we've now figured out the first derivative of y with respect to x in terms of t. Now, how do we find the second derivative? How do we find the second derivative of y with respect to x now? And I'll give you a hint. We're going to use this same idea. If you want to find the rate of change of something with respect to x, you find the rate of change of that something with respect to t and divide it by the rate of change of x with respect to t.
So you did it with the first derivative. You go, we're going to find the rate of y with respect to x. So you do derivative of y over the derivative of x. Well, if you're going to do the rate of the rate, if you're going to take the derivative of the first derivative, well, then you want to take it with respect to dx dt again. You want to do that every single time. You want to stay consistent.
So what this is going to be, we want to find the derivative of the first derivative with respect to t. So let me write this down. So we want to take the derivative with respect to t in the numerator of the first derivative, which I will put in blue now, of dy dx, all of that over dx dt. Now I want you to, if it just...
That's the extra piece right there. Take the derivative of the derivative. See, we don't have to worry about it if it says 1/2 e to the x. If this says 1/2 e to the x and then we take the second derivative, we are taking it with respect to x. But if it's in terms of any other variable, you're not taking the derivative with respect to x. You're taking the derivative with respect to t. So if we want the second derivative with respect to x, we got to somehow get that x in there.
If it doesn't jump out at you why this is the same thing that we did before, I encourage you to pause the video and think about it.
All right, that's good.
Think about what we did over here the first time. When we wanted to find the derivative of y with respect to x, we found the derivative of y with respect to t, and then divided that by the derivative of x with respect to t. Here we want to find the derivative, we want to find the second derivative of y with respect to x. Actually, let me just write it down out here a little bit clearer. What we really want to do is we want to find the derivative with respect to x. When we wanted to find the derivative with respect to x of y, that was equal to the derivative of y with respect to t over the derivative of x with respect to t. Now, we want to find the derivative with respect to x of the first derivative with respect to x. And so everywhere we saw a y here, replace that with the first derivative. So this is going to be equal to, in the numerator, the derivative with respect to t of dy.
He's kind of repeating himself, but that's good. That's good. He's saying, listen, I'm taking the derivative of y, but I'm not taking the derivative of x. With x is not involved in this. How am I going to get that in there? Well, you end up dividing by dx dt.
This is the derivative with respect to t of y. So hopefully you see, before we had a y there, now we have a dy dx, dx dt. Now this might seem really daunting and complicated, except for the fact that these are actually fairly straight things to evaluate. Taking the derivative with respect to t of the first derivative, well, that's just taking the derivative with respect to t of this. And this is pretty easy. This is the derivative was just going to be 1/2, and the derivative with respect to t of e to the t is just e to the t. And so that's going to be over the derivative of x with respect to t, which we already saw is 6e to the 2t. 6e to the 2t. And so we can write this. We can write this as, let's see, 1/2 divided by 6 is 1 over 12, and then e to the t minus 2t, which is equal to, we could write this as 1/12 e to the negative t, or we could write this as 1 over 12 e to the t. And we're done.
Okay, and that's where he ends it. Very good. All right, hopefully that emphasizes it. Hopefully hearing it from someone else helps. And let's practice it now. So we're looking at exercise 8 and 10 out of the book. And it says find the first derivative and find the second derivative. We're not doing anything with it, we're just finding it. For letter A, the first derivative, dy over dx, is the derivative of y is, let's do this, dy dx is equal to negative square root of 3 sine of t, and then the derivative of x is negative sine of t, and we cancel as we go. So those cancel, and you're just left with the square root of 3 for the first derivative. B, the second derivative, is 0. That's the derivative of the first derivative over, and I know it doesn't matter what's over now because it's 0, but if we did a complete problem here, we'd have it over negative sine of t, dx again. And it ends up just being 0, though. Try number 10, if you will. It's got a little tricky algebra in it. See the first derivative. Let's do this. 1 over t over, and the derivative of t to the negative 1, which is sitting right here, negative t to the negative 2. So that's negative 1 over t squared. So there's a derivative of y over derivative of x. Now instead of dividing, let's multiply by the reciprocal. So I'll take that, I'll change that to multiply by the reciprocal. So negative t is the first derivative. B, d2y over dx2 is negative 1. That's the derivative of the derivative of negative t, but then over derivative of x, which is negative 1 over t squared. So you have to divide by the derivative of x again. Multiply by the reciprocal, you just get t squared for the second derivative. Everybody good with that? All right. Sketch the curve over the given t interval, indicating the direction which is traced. Identify the requested point, which in this case is the leftmost point. And they're saying, well, use the calculator to see if you can kind of get an idea of where it is. And then letter C will actually find it. So let's go letter A. Y equals. Let's clear these out. T squared plus 2t. And then t squared minus 2t plus 3. From negative 2 to 3, window, negative 2 to 3. What about the negative 7, the 7s and the 4s? Let's see if that works. If it doesn't, we'll adjust it. Graph. And it doesn't work. I think if I remember right, let's go, I don't know, negative 2 to 10. I think it's more than that. I think it's negative 2 to, let's go to 15. And the y, let's go from negative to, how about to 15 again? Oh, yeah, I'm down here. Delete off of that, and that's 1. Negative 2 to 15. Let's see what that looks like. I'm looking at the leftmost point, so I don't know if I'm far enough to the right. We'll call that guy, It might have stopped. I don't know. It doesn't matter. Anyway, it looks something like that, let's say. Indicate direction. B, let's hit trace. T is -2 and we're going from -2 to 3 to see where the leftmost point is. I don't know, what do you think right here? Yeah, that seems reasonable. Now I will tell you that it's a nice point. So it's actually -1, 6. I would never ask you to actually do this on a test. Just go, oh, hit trace and see what you get. Sorry, you're a decimal point off. You know, I'm not going to do that. But for the purposes of this, here's our guess. Now, if we're going to go leftmost point, we're going to minimize the x. X is left and right. Y is up and down. So we're going to the left. We're going to minimize this. So dx dt is 2t plus 2. Set that equal to 0. T is -1. -2 divided by 2. So the t is -1 when we're to the left. But where is that? Now we're going to take this and we're going to plug it in to actually find the point. 1 minus 2 is -1. 1 plus 2 is 3, plus 3 is 6. So it was actually -1, 6 is the farthest left point. And we could have done it here too. Calculate a value -1, -1, 6. Exact same instructions, but let's work with some trig a little bit. See what we can get out of this. Let's go with A. Let's sketch it. We'll clear these. Tangent of x, or t in this case. And then we need 2 secants, so 2 divided by cosine. We don't have a secant button. This is a fairly small graph. I just happen to know what it looks like because this is the 3rd time I'm doing this today. So I can kind of, hopefully I remember right. First of all, the t's are -1 to 1. And it's a small graph. So let's go from, how about -2 to 2. And I think if you go from 0 to 4, I think it fits. If it doesn't, we'll adjust it. Yeah, that seems very nice. Nice window. It's a small graph. Let's sketch it. Looks like that. The lowest point seems to be 0, 2, and that's, as a matter of fact, that's what it is. It is 0, 2. I don't even need to, well, I can just look at that and know probably what it is. It could be 0, 1.9, but it's not. It's a nice value, by the way. Lowest point is minimizing the y. So dy dx, excuse me, dy dt, that's a habit, dy dt is equal to 2 secant tangent. But we got to set that equal to 0. Let's talk about secant. From -1 to 1. From -pi/2 to pi/2, cosine looks like this. And secant's a reciprocal of cosine. So secant is doing this action. So secant, it's impossible for secant to be 0. Secant cannot be 0. Like, think of it this way. What does cosine need to be to make 1 over cosine 0? Can't do it, right? Can't be 0. Can't divide by 0. All right, so secant can't be 0. That doesn't give me any solutions. But tangent looks like this. So t equals 0. Tangent of 0 is 0. But I need a point. I need to plug this in for each of these. So the point is tangent of 0 is 0. Secant of 0 is 1. It's sitting right there. It's 1. So the lowest point is 0, 2. There we go. Good stuff. Good stuff. How about a little twist on this? Let's find the points at which the tangent line to the curve is horizontal or vertical. And I've already graphed it over here just to pick up the pace a little bit. It looks like the horizontal tangent lines are right here and right here. And it looks like -2, 1, 2, 3, 4, -2, 4, and -2, -2. And that is what it is. That's actually the answers, but we need to be able to get those. We want the derivative, or the dy dx, the slope. The derivative of y is 3 cosine, and the derivative of x is -3 sine of t. And I can ignore the 3's. For horizontal, for letter A, I need the top to be 0. Horizontal has a slope of 0, so I got to make the slope 0. So I need cosine of t equal to 0. Now we're going from 0 to 2 pi. There's no need to go from 0 to any farther than that because that's one trip around the circle. So t is equal to pi over 2 and 3 pi over 2. That's where cosine is 0. So we'll plug each of those in to find the points. Cosine of pi over 2 is 0, so it's -2. Sine of pi over 2 is 1, so -2, 4. So -2, 4, that's this point right there. There's -2, 4. When we plug 3 pi over 2 in, cosine of 3 pi over 2 is 0, so -2. Sine of 3 pi over 2 is -1, so it's 1 minus 3, -2. So there's -2, -2. That's that point down there. So there's where the tangent lines are horizontal. Letter B asks where the tangent lines are vertical. And we even know what those are. It's I think it's 1, 1 and -5, 1. Those are nice points. But now we want the denominator to be 0. And that negative won't change what the zeros are. So I don't really care about that negative. If you want to put the negative in, just divide by -1, and there it is. There it's gone, right? You can ignore that. So t now is equal to 0 and pi. That's where sine is 0. That's what would make the denominator 0. That's what would make those vertical tangent lines. Now when we plug 0 in, cosine of 0 is 1. -2 plus 3 is 1. Sine of 0 is 0, so 1, 1. There's 1, 1. There it is, right there. And then the other point, plug pi in. Cosine of pi is -1, so -2 minus 3, that's -5. Plug pi in over here. Sine of pi is 0, 1. So there's your -5, 1 right there. There's where the tangent line is vertical. Takes a little while to explain, but it's really not that tough. Just top and bottom, make top and bottom zeros. You got it. And then finally, we're going to end with finding the distance of a curve. And like I said before, we could probably do this with one big one big triangle. But that wouldn't be a very good estimate. We want lots of triangles with really tiny hypotenuses. And that's what integral does for us. So we're going to integrate from 0 to 3, square root of, I need the derivatives. So dx dt is 1. So 1 squared plus derivative of y is 2t. So 4t squared dt. With this one, there's no way to get rid of the radical. There's no nice perfect squares under there. So this is a calculator problem. However, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this doesn't curve a whole lot, does it? Wouldn't you expect that length to be somewhere around 9? Does that seem reasonable? Since it's not doing a lot of curving. Now, if this curve did this, that'd be a lot more than 9. There's a lot of curving. There's a lot of distance traveled there. But it seems like this should be about 9. Math, 9. 0 to 3 of square root of 1 plus 4 something squared, t squared in this case, who cares? And there we go, 9.747. 9.747, it's an answer that I felt, I feel comfortable with. Because it seems like it's not much more than 9 anyway. There's not a lot of curving. It's practically straight. So that makes sense. All right, there you go, you guys. There's the calculus that goes along with the parametric.